What will we do without Mina? Sheesh. All right. So yeah, definitely about microwave background radiation. Read everything about it. Like what is it? Why is there? What is the meaning of it? That picture of the background radiation. What's the meaning of it? Right? It's like there's red spots, yellow spots, blue spots, dark spots like that. And if you look around, you can see it everywhere, right? Doesn't matter which direction you look, it's all over the place. It's the background radiation, the leftover from the Big Bang and all that. So the background radiation is pretty importante. All right, then the age of the universe, the size of the universe, right? That's going to be one of the questions. Then there'll be questions on the, I'll just wait for you guys to finish writing it down. Be questions on the Andromeda galaxy. So what is Andromeda galaxy? How far away it is? What's going to happen in 4 billion years or 5 billion years? It's going to collide with the Earth and all that, right? The Andromeda galaxy. So there'll be a collision sometime in the future.
How old and how large?
How old you wouldn't know, but how large? No, I'm not going to ask you questions like that either. Let's see. There it is. There's the Andromeda galaxy. It's going to collide with the Milky Way galaxy in about 4 to 5 billion years. And what's going to happen is like once we collide, there's going to be a period where we're going to lose our spiral arms, and then finally the black holes collide. Like these two galaxies are colliding, and that's where elliptical galaxies come from, right? From collision between spiral galaxies. So once you collide, you're losing your spiral arms. You can see what happens. Bang, right? You go through bangs and bangs. So you collide, and then the bulge is still there, but you're losing your spiral arms. And the black holes merge. That's it. So, okay, so the Andromeda galaxy and the active galaxies, right? The active galaxies.
Did you say a black hole emerges or the black holes emerge?
I didn't say emerges. I said they merge.
Oh, thank you.
Their black holes merge. Yeah, sure thing. Let's see. Galaxy collision.
So it was that the black holes merge and that the spiral arms, you lose them?
Yeah, so the cores are kind of laid bare. That's what elliptical galaxies are. So elliptical galaxies, well, I'm just going to go over it. So just have a little patience. We'll get there. So what is this? So you guys recall what this is? Oh, let's see. Give me a second. I got to share it with you. You guys see this? This is what we call a quasar, right? What's the quasar? It's an active core of a galaxy. There's supermassive black holes in all of galaxies. And some of them are active, some of them are not active. If they're active, you can see them from far, far, far away, right? And we call them quasars. If they're not active, they'd be just like Milky Way. Our galaxy is kind of sitting there, doesn't do anything. The black hole just sits there, and it's very inactive. It's quiet. You can't see anything. But because we can see this from far, far away, we couldn't figure out what these are until recently when Hubble Space Telescope took pictures of these cores of active galactic nuclei. And now we can see this gigantic amounts of energy being released from the core of these galaxies because there's so much gas and dust falling into these black holes. So these are active black holes. We can see them pretty far, far away, like end of the universe, we can see them.
So if the supermassive black hole is active and we can see them, that's when we call it a quasar. If it isn't active, it would be just a galaxy.
Well, you wouldn't be seeing it.
You like the
Yeah, that would just be something you can't see.
Got it. Thank you.
Faraway galaxies are faint, so the only way you can see it is if they're active. Yeah. All right, so let's see. Question I have from you is this. Let's see if you guys can figure this out. So when I look at the moon, I see the moon the way it was a second ago, right? I don't see it right now. If I look at the sun, I see the sun the way it was 8.5 minutes ago. So let's say I have a telescope and I look at a faraway galaxy. Let's say it's 12 billion years old. Now the universe is only 13.8 billion years old. So if I look at a galaxy that is 13 billion light years away, am I looking at a young galaxy or an old galaxy?
A very
What do
young
I
galaxy.
see if I look at it? I'm sorry?
A very young galaxy.
A very young galaxy that was just born yesterday. So I'll see a baby, right? I see a baby galaxy if I look at something that is very far away. Is there any questions on that? You guys follow what I'm saying? Good. All right. Excellent.
You said the age of the universe is 13.8 billion years?
Yeah. Who's asking all these questions?
That was just me. Lourdes?
That's Lourdes?
Hmm.
Okay, Lourdes. I think it's like the second time I've ever seen you, Lourdes. Sheesh, Lourdes.
I had to for the last class.
Yeah. All right, so I'll give you a question on inflationary Big Bang universe. So there's a lot of questions on inflationary Big Bang universe. And I'm not going to go over it again in detail, but basically, when we had the Big Bang, what caused the bang in the Big Bang?
Gravity was reversed.
Very good. I'm guessing who this is. Let's see. Is this Carson?
It was Trevor.
Trevor, yeah. Yours, this sounds just like Carson. Thank you. That's right. Exactly. So can you elaborate on that, please?
Yeah, so gravity reversed for, I believe it was 10 to the minus 35 seconds. And during that time, that's what started the expansion of the universe. And then after that, dark matter is responsible for the
So that's
acceleration
the Big Bang. Dark energy, not dark matter. Dark matter is like regular matter, except much heavier, right? And so that's got a lot of gravity. So at first, that inflation was caused by gravity of matter acting in reverse. That's when it went like that. It went, and then it kind of coasted for a while like that, right? So, like in a blink of an eye, the universe was as big as the Milky Way galaxy, right? That's how big the Milky Way was. Now, if the universe was as big as the Milky Way galaxy, what does that mean for the expansion of the universe? What does that mean for the speed of light? Means that space was expanding a lot faster than the speed of light, right? So in that case, the speed of light was probably, gazillion times the speed of light that we see today. It was a different time. That's the inflationary Big Bang theory of the universe. So then this dark energy is taken over right now. We live in a place where dark energy is taken over. So everything is accelerating in expansion. So it went like that. It became gigantic. Then it kind of coasted. And then when matter was kind of diluted in the space itself, now there's a lot of space. So the dark energy in space is going to make it go again, right? It's going to, so, and then coast, then again like that. So what's going to happen at the end of the universe? What is that going to be like? There'll be a question as to what's going to happen at the end of the universe too. Now, I suggest you guys watch the video of the Milky Way, and then after the Milky Way video, the Milky Way class that we had a couple of weeks ago, we had 3 classes where we talked about cosmology. You should study those 3 45-minute videos. I'm suggesting to you, watch those 3 45-minute videos, and then you pretty much get everything, right? So that 1 15-minute video, the Milky Way, that gives you about 50% of everything. And the rest of it, you should watch those 3 videos, because I'm not going to have time to make you guys videos last minute. And you can find those videos. It's all in your inbox.
Those
Camp-
3 lectures were after what?
After Milky Way.
Thank you.
When I was done with the Milky Way, then everything became cosmology. All right. So let's get going. I'm going kind of slow. All right, so you should study the picture that I showed you before, all the stuff about classification of galaxies. I think there's like 3 questions on classification of the galaxies. So the classification of galaxies, you're looking at the properties of these galaxies, like the properties of the elliptical galaxies. There's 2 kinds of ellipticals. One of them is dwarf ellipticals, tiny dwarf ellipticals that are all over the place next to us. Like in our neighborhood, there's plenty of dwarf ellipticals. And then there's giant ellipticals too. And they all come from collisions between giant spiral galaxies. So once they form, these are the properties, right? They only have population 2 stars. That means old stars. And a tiny star like nuclei. They have a little itsy bitsy nucleus. And they have no dust or gas or spiral arms. And then we get to the lenticulars and the spirals. So spirals and lenticulars are the same kind of galaxy, same properties, except lenticulars don't have any spiral arms, or they'd be called spiral galaxies. And these are the properties of these 2 kinds of galaxies. So they have population 1, population 2, population 1 young, population 2 old stars. They have a lot of dust and gas. That's how you make stars. Why do these elliptical galaxies have no young stars, population 1? Because they don't have any dust and gas. So they have no dust and gas, therefore they can't make any new stars. And then these guys also have, obviously, spiral arms. They have a big bulge in the center. And so that's it. Population 1, population 2, lots of dust and gas. They have a flat rotating disk, gigantic nucleus. So now there's 2 types: regular spirals, normal spirals, and then barred spirals. The difference is in barred spirals, the spiral arms come from the end of the bar. So there's a bar of dust and gas going through the center. These guys come from the end of the bars. Here they come directly from the bulge or nucleus. That's the difference. And then how big this bulge is or nucleus is determines whether they're A, B, or C, and also how tightly wound up the spiral arms are. So if they're really tight, SA or SBA. Smaller nucleus, a little looser, it'll be SB or SBB. Really loose, spiral arms are just wound up, wound out, I guess. I don't know what the word is. And so is the SBBC and SC. So these are all pretty much the same. And our galaxy is SBB.
SBB.
Yeah, right. So now, irregulars, what the heck are they like? They have no nucleus at all, and that's the key thing. They have no nucleus, no spiral arms, but they do have young stars and old stars. So if they have young stars, that means they have dust and gas. That's what it means. All right, so that's going to be 3 questions on that little diagram I just showed you then. All right, let's see. Make sure you understand what cosmological principle is, please. Please make sure you read about the Hubble's law. The Hubble law.
I'm sorry, what'd you say? Cosmological.
Principle. Cosmological principle. De Hubble's law. Then where do we live, basically? Where is the Milky Way galaxy? Milky Way galaxy is in a local group of galaxies at the edge of Virgo cluster of galaxies, or Virgo super cluster of galaxies. The Virgo cluster of galaxies then is a part of a much bigger structure called Laniakea, right? Which means immeasurable heaven in Hawaii, in Hawaiian. What a cool language. You know, they only have like so many letters, right? Very few letters, but they're making all these cool sounds.
What was that word again, Professor?
Laniakea?
Yeah.
Yeah, I even showed you. If you just watch those 3 videos that I told you, there's a whole bunch of videos on Laniakea that I got in there for you. Lania, 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 Kea, Kea, Laniakea. And then Laniakea is a part of those filaments that we talked about, right? Okay. So there'll be a question on this thing that we talked about, the finite and boundlessness of our universe. So what does that mean, finite and boundless? Means that there's no end to it. Even though there's only so much space, you'll never get to the end of space. And there'll be a question on the two-dimensional universe that Carl Sagan talked about. Remember the 4th dimension? He talked about a surface. You walk around the surface and you never reach the end. So it's finite and yet it's boundless. So how is it finite and boundless? Well, it's the surface of a sphere. So it's two-dimensional. Surface of a sphere is two-dimensional, but there's no end to it, right? So it's finite. There's only so much surface, but it's boundless. So there's no end. But it's surrounded by 3rd dimension. So our universe is surrounded by 4th dimension. That's what's outside of the universe, is higher dimensional space.
So if the 3-dimensional and the 2-dimensional are both finite and both boundless, is there a place that would be infinite?
I never said what you're saying. I'm sorry. I never said that.
Oh, no?
I said no. I never said that. I said, see, the way you're saying it is like all two-dimensional surfaces are finite and boundless. That's not true. Like the top of my table is two-dimensional.
Mm-hmm.
But it's not finite and boundless. It's finite, but it's not boundless. Like my cell phone falls off the table. That's not boundless, right?
Oh, okay.
Do you understand? Yeah.
I have a question too.
Yes, please.
Can you think about it as like in a sphere, they're having infinite amount of points in a sphere? Can you think about it like that, being boundless?
On the surface of a sphere?
Yeah.
I guess. Do you think there's infinite number of points on the surface of a sphere?
Yeah, I do.
Okay. Well, then yes. The answer will be yes.
Okay.
Anything that helps you think is good for you. It's good for me, you know, if that's the way you feel about it. Personally, I don't even think there's a point. Point doesn't exist, right? What's a point? I mean, you know, a point is like, you put a little dot on the board, that's a point. But it's not really a point. It has thickness, it has, you know, everything. So, I don't know, geometry to me is kind of like made up, you know, line is one dimension. And yet, I've never seen a line that has no thickness, right? You see what I'm saying? Okay. Yeah, there's so many questions on the microwave background radiation and these active galaxies. So how did matter form in the beginning of the universe? Where did you and I come from? Because there was only energy after the Big Bang. So what happened? Well, there was particle pair production, right? Gamma rays came together, and then they brought out stuff from from vacuum, basically, right? Virtual particles came into existence, like an electron and a positron. So what is empty space? Now let's see, I guess I gotta go the other way. Empty space looks like this, right? Empty space is full of virtual particles. Virtual particles live in a vacuum. So this is a vacuum. Does that look empty to you? No. So there's an electron and a positron. They just came into existence. But as soon as they exist, they annihilate each other and they go out of existence. So they give out energy. So there's no such a thing as a real vacuum in the universe. It's like full of virtual particles. So when you have those photons, gamma ray photons that have so much energy, depending on how much energy they have, they can bring out matter into the real universe, but in a pair, like an electron and a positron, a quark and an anti-quark, like that. Quarks make up the nucleus or the proton. Okay, so that's what empty universe is, empty space. Okay. So we already said Hubble's law. So what kind of galaxies populated?
Sorry, you said a quark is, I'm sorry.
I said a quark and antiquark. So what I showed you was a vacuum, right? It was a vacuum, but it's full of virtual particles. That means particles and they're antiparticles. Like an electron has an antiparticle. So for every particle, there's an antiparticle, like a quark, antiquark. A muon, an anti-muon, an electron, and a positron, like that. A muon is like a heavy electron.
Thank you.
You're welcome. Okay, how about at the beginning of the universe, what kind of galaxies did we have? Let's see if I can find that video. Let's see, I think it's here. No, it's not here. So where is it? Okay. All right. So when we look at like the farthest thing in the universe, we see the youngest galaxies of all. And what do we see? We see spiral galaxies everywhere, right? Spiral. They're all spiral galaxies. We don't see anything else, right? So the very first galaxies that came into existence were like the Milky Way. It's spiral galaxies. That's what it looks like at the very beginning of the universe. This is the very first galaxies that came into existence. Right. So where did the elliptical galaxies come from? From the collisions between these beautiful spiral galaxies. Wow, man, there's so many questions on that one diagram that I showed you on the classification of galaxies. And also the background radiation. Right. Okay, what about inflation? What is inflation? At the beginning of the universe, there was inflation, right? So right after the universe came into existence, for a very short period of time, I remember somebody at the beginning of the class said 10 to the minus 35 seconds, remember? So it was between 10 to the minus 33 and 10 to the minus 35 seconds, very short period of time. Matter acted the opposite. Gravity, instead of attracting, just made everything repel. That's the beginning of the Big Bang, basically. Now, that's inflation. It means there was so much energy, and that energy was acting, that gravity was acting like in reverse. It was repelling instead of attracting. And so there's other places in the universe that do that right now as we speak. And so we say this inflation is eternal. There's like other parts of our universe where this inflation is still going on. That's why we think there's like other universes being born. That's why we think there's multiverse, more than one universe, right? So maybe this is our universe. We have like a whole bunch of universes that were born before us, after us, and there'll be more and more and more, probably infinite number of universes.
I have a question about that.
Yeah.
Do we have any way of telling where this inflation is still happening or why it's happening?
Most likely not, because those places are probably so far away, they'd be outside of the observable universe. Do you remember the observable universe was only 46 billion light years in radius? So it's most likely outside of that. We can't see it.
So they just assume that this is happening based on something that's happening somewhere else in the universe. They take readings somewhere else. And
No, they assume from the fact that there was inflation in our universe. And when you look at the equations of inflation, they show that it doesn't stop. Once it begins, it never stops. So
they think it just moves somewhere unobservable. And so
there's places in the universe where there's a lot of energy, unused static energy, imagine, right? And those places can give birth to a new universe. So new universes are sprouting up. We probably were the same thing. We probably came off another universe. So at the beginning, what we call a Big Bang was just like an ordinary event in some other universe that happened,
Cool.
So we're not even special in that sense. We're always trying to make ourselves special. Yeah. Go ahead.
Oh, I just said that's wild.
Yeah, Trevor. Yes. All right. So then we get to the Milky Way. Milky Way is going to collide with which galaxy in 5 billion years?
Andromeda.
Andromeda galaxy in 5 billion years. That's right. So we're going to be colliding. So like if you come back to Earth, like, I don't know, in 5 billion years through your soul coming back to another body, you look up in the sky, you see this beautiful, gigantic galaxy getting close to the Milky Way, and we're going to be a collision. Nothing is going to survive that collision. So that's tops. The entire Milky Way galaxy will live for at least 5 billion years. Then it's going to be hell. Yeah. It's a slow motion hell, though. Slow motion hell means we're going to be kicked out of the Milky Way, but it'll take 100 million years for us to happen. Okay. So now we get to the Milky Way itself again. So how long does it take the Milky Way in the Milky Way for the Earth to go around the galaxy one time? How big is the Milky Way? How far away is the sun from the center of the Milky Way where the black hole is? So the statistics of Milky Way, that 15 minutes should give you all the information you need. And then so what holds us for, we're going around the sun every 225 million years, but we're going really, really, really fast. What's holding us in? Why are we getting ejected? Why are we just getting kicked out?
Gravity?
No, it's not gravity. Starts with a D. Starts with a dark. Dark something.
Dark matter.
Dark closet, did you say?
Dark matter.
I thought you said dark closet. Dark closet. Do you guys still check under your bed before you go to bed? Just to make sure there's no monsters under your bed? I only start checking, I don't know, just a while back, like just a few years ago. Linda, you check under your bed, huh?
No.
Just kidding. Okay. All right, so like what are the populations? Population 1, young, and only in the disk of the galaxy. So everywhere else, population 2. Population 2 stars are in the bulge of the galaxy, they're in the halo of the galaxy, they're in the globular clusters of the galaxy, like that. Let me show you, let's see. Oh, I gotta go somewhere else altogether. I gotta go to the Milky Way. Milky Way, Milky Way. Huh. Oh, here it is. All right. Okay, you guys can see this one. So these are the globular clusters, right? They live in the halo of the galaxy. They live all the way around, like bees around the beehive. And then they orbit the galaxy perpendicular to the disk. There is the disk of the galaxy. And this disk is also called a plane of the galaxy, Plane. And we also refer to it as the
Zone of avoidance?
Avoidance, that's right. And why do we call it the zone of avoidance? What's avoiding this disk of the galaxy?
We can't see the other part of the universe.
That's right. So when you look in here, all we see is dust and gas. So if you want to see what's out, what other galaxies are out there, you want to look this way, perpendicular to the disk, just like the orbit of the globular cluster is perpendicular to the disk. This is along the disk. This is perpendicular to the disk. Okay. And then there is, oopsies. There's a halo of dark matter that surrounds the galaxy, right? Like that. Again, I suggest you guys watch that 15 minutes. It'll give you like 20 more points on the exam if you learn that stuff. So here's where the globular clusters are. This is where the dark halo matter is. And it's got gravity. We can't see it, but it's got gravity. 5 times more gravity than regular matter. So that's what's holding us in. Otherwise, we'll be ejected out of the galaxy. We'll just fly out. So we go around like this every 225 million years. And that's still pretty fast. We'll be ejected out of the galaxy. Okay. Next question. Almost done. So if I ask you like this part of the galaxy, that part of the galaxy, what population stars they are, you always say population 2, unless I ask about the disk or the plane of the galaxy. That's where the stars are born. Everywhere else, population 2, old guys. So where do the new stars in the galaxy, Eva, where are the new stars in the galaxy being born?
Not in the plane. Sorry.
In the plane.
I was going to ask you to repeat it. I was trying to write it down and I got confused, but in the plane.
That's right. Only in the plane we have young stars. That's right. Sheesh. All right.
And the disk, right?
The disk is the plane.
Oh, yeah, duh.
That's another word for the plane. All right. So what are the proportions of dark energy, dark matter, regular matter, right? That's something you need to know. Like 4% is regular matter. 23% is dark matter. We're talking about the mass of the entire universe. And then the rest of it is, like 74% is space itself, right? It's dark energy. So dark energy makes up almost 75%. The other 25% is mostly dark matter and just a little bit of regular. So me and you are just an exception. We're not making up the universe. The universe is basically made of dark energy and dark matter, with us being just 4%. Like all the galaxies, everything that we think is fantastic, it's only 4%. Sheesh. So yeah, we all need to have a more respect for space itself. All right, what are the Magellanic Clouds? You need to know like what kind of galaxies they are, where the heck are they? These Magellanic Clouds, they orbit the Milky Way galaxy. They're irregular galaxies. They were named after Magellan, the circumnavigator. All right. So what's the closest major galaxy to the Milky Way called?
Andromeda?
Yeah, I heard you, Linda, even though your sound is mute. You said Milky Way, you said Andromeda, right? Yeah, you said Andromeda. You can leave your microphone on if you're not having a party in your room.
Well, I have 3 dogs, so I never know when they're gonna go off.
Oh, well, maybe the dogs will answer the questions. They're pretty smart.
Yeah.
My dog is really smart. He watches Oprah.
Awesome.
Yeah, pretty cool dog. I'm lying. He doesn't watch Oprah. He watches Lassie. He loves Lassie.
Lassie.
So now, what's the closest galaxy to the Milky Way?
Andromeda.
No, that's the closest major galaxy to the Milky Way. The closest galaxy is
Sun. No.
Sunjun. No, it's not Sunjun, but it's Canis Major Dwarf Galaxy. This was the closest. Just watch the 15-minute video. I think it's in there. But yeah. Sheesh. What are open cluster of stars? You need to know that. And where are they? And what are open cluster of stars?
And I'm sorry, what was the closest galaxy's name?
Canis Dog Major, the big dog galaxy. See, I told you dogs are important, Linda.
Open cluster of stars.
I should tell your dog. Is Canis Minor. All right, so what happens in the H1 regions of the galaxy? That's also in that 15-minute video, the H1. Remember, the electrons are spinning one way, then they stop, and they spin the other way. They send out a radio wave telling us of their existence. Amazing. Make sure you understand where the H2 regions are and what's going on in there too. So H1 is where there's nothing happening. It's just neutral hydrogen clouds are sitting there and sending out these radio waves every few million years. An atom will do that. But in the H2 regions, it's like, star building is going on all the time. There's like ionization of the gas. The stars, when they're born, they heat up the gas, they blow away the gas. Again, that 15-minute video will give you a lot of the answers. Okay, all right, almost done. So how big is the Milky Way galaxy? From end to end, from the end of the spiral arm to the end of the spiral arm, it's about 100,000 light years. So if I shine a flashlight, it goes from one end to the other end in 100,000 years, right? So when I say 100,000 light years, it's a measure of distance. So how long does it take light to travel 100,000 light years? 100,000 years, not 100,000 light years. Light years is distance, right? So time is years. There's a difference, huge difference. All right, so what happens in a spectrum of a galaxy when it comes towards you, when it moves away from you? We're talking about redshift and the blue shift of the galaxies. So if I'm shining a flashlight and I'm moving towards you, my yellow flashlight turns blue. If I move away from you, my flashlight turns red. So when we look at the farthest things in the universe, the galaxies are moving close to the speed of light. So they appear to be reddish, even though they're not really reddish, they're kind of like yellowish or something, but they appear reddish. So approximately how long ago was the universe born? What's the age of the universe again? It's 13.8 billion years. All right. See, I think we're done. We talked about empty space. The one thing we didn't talk about is what is the expansion of the universe? What does that mean? The universe is expanding. What is expanding?
It's the expansion of space?
That's right. It's the expansion of space. And how does space expand? Right? Like, Lourdes, your pocket is the center of the universe. Why?
Because everything's moving away from there?
That's right. Because everything in the universe is moving away from your pocket. That's right. Very good. Okay.
Can I ask a question real quick?
Of course.
So I was just a little confused about the whole light years thing. So one of the review questions is how long does it take light to travel a certain light year distance? So then the answer to that is that 100,000 years?
No, that's how long it takes light to travel 100,000 light years. That's the diameter of the galaxy is 100,000 light years. Okay. So tell me, how long does it take light to travel 1 light year?
I'm not sure.
1 year.
Oh.
You have to understand, please don't miss that question, Lourdes. So a light year is how far light travels in 1 year. So how long does it take for light to travel 2 light years? What's the distance is 2 light years? How long does it take to travel 2 light years? 2 years.
Okay.
How long does it take light to travel 10,000 light years?
10,000
years. There you go. Yeah, like that. All right, let's see. More background radiation questions. Oh, geez. There's a lot of questions on those quasars, the active galactic nuclei. Yeah, there's a lot of questions on that. So my suggestion to you is watch the 15-minute video. Watch those 3 videos after that, Milky Way. And you should be good. You should be good. Normally, people do their best scores on the last exam. It's the easiest of all the exams. You can pretty much answer it right now. You could probably take the test and do well. So don't get nervous. Just relax. You should be all right. You guys will be good. Anyways, thank you so much, you guys, for trusting me. You know, you guys seem like you trust me. Anyways, if you don't show it. So thank you so much for trusting me and respecting me. You didn't make fun of me. That's good. You should have made fun of me, but you didn't.